So this brings us to the divergence theorem. This is the statement of divergence theorem, and again, there are a lot of conditions that go into this theorem, and I'm not that concerned with most of the conditions. Let W be a solid in R3, so in my head I'm visualizing W as like a box or a sphere, and the boundary of W is a piecewise smooth closed surface. And it's exactly what we've been talking about in terms of boundaries before, only in this case it's the boundary of the whole surface, of the whole volume, which means that the boundary of a volume is going to be the surface, like the shell of the sphere. And that surface is oriented so that the normal vectors to that boundary point outward. Outward pointing normal vectors, that's standard. Also, let F be a vector field whose domain contains W, that's sort of course, otherwise it doesn't make sense, and F has continuous partial derivatives. Again, this is something that we aren't going to check. Most of the nice functions that we're dealing with have continuous partial derivatives. If you don't have continuous partial derivatives, problems happen. This is the statement of the theorem. Then, what do we get? We get that the surface integral of F, our original function F, over the boundary of W, so this is when I take the surface integral over the boundary of the sphere, that's going to be exactly equal to the divergence of F computed as a triple integral over the entire solid sphere. So this theorem is very similar to some of the theorems that we saw before, only the previous theorems that we were looking at, we had boundaries that were just lines, and then we were setting them equal to double integrals over surfaces. And now we have a double integral, which in this case is a closed surface, and it's going to be set equal to the triple integral of the divergence of F over that entire volume. There are a couple of things that I want to point out. First, let's point out how do we actually compute each of these pieces? And second, how does it relate to some of the things that we've seen before? So I'm going to put up on the board all of the previous theorems that we've looked at. So here are our three big theorems. Green's theorem is telling us that the line integral over the boundary of some region D in R2 is equal to the double integral over that region D of the scalar curl of that function F. So why do we know that we can apply Green's theorem? Green's theorem only applies when F is in R2. It's a two-dimensional, these are flat. This is a flat region down in the xy plane. Whereas Stokes' theorem is exactly the same theorem, only instead of being flat in the xy plane, we're up, F is in R3. That our surfaces now can be these curvy surfaces up here in R3. And then finally, with this divergence theorem, we've gone up a whole nother dimension. That our F function is still typically in R3. F in R3. But instead of being interested in computing something along a linear boundary, because these are all line vector integrals, now we're looking at the double integral over a closed surface being equal to the triple integral over the volume of that surface. So the primary difference in these two pieces is the fact that my F is only in R2 for Green's theorem, whereas my F might be in R3 for Stokes' theorem. And then as we go up to the divergence theorem, we've added another dimension. One thing that I do want to point out is the fact that this piece right here is a surface integral in Stokes' theorem. This piece right here is also a surface integral. But for this surface integral, it could be any surface that we want. It could be a flat magic carpet surface, it could be a cylinder, but these surfaces have to be boundaries of volumes that are solid. So for the divergence theorem, my surfaces have to be closed. Hopefully that's sort of a big overview of what we're looking at with these three major theorems in chapter 17. And now, let's go ahead and do an example. of the divergence theorem.